We spend so much time talking about how to make things go faster, stronger, more efficient. But what about the other side of that coin? How do we make things stop? Today, we're diving into the hidden world of motor braking. And trust me, it's way more fascinating and complex than you might think.
So, here's what we're going to cover. First, we'll look at why stopping is a problem in the first place. Then we'll see how braking is really an art of control. We'll explore the two main ways we do it, see where they're used in the real world, and wrap up with why all of this is so incredibly important.
All right, let's jump right in. Getting a motor to start seems pretty straightforward, right? You give it some juice and it goes. But stopping? Well, stopping is not as simple as just cutting the power, not by a long shot. And that leads to the big question here. If starting is just a matter of go, why is stop so much harder? What's the hidden force that makes bringing a heavy spinning motor to a halt such an engineering challenge? Well, the answer comes down to one simple word: inertia. That law of physics that says an object in motion wants to stay in motion. A motor spinning at thousands of RPM has a ton of inertia, and it doesn't just give up because you turned off the switch. It's going to fight to keep on spinning. And if you just let inertia have its way, well, things get ugly. An uncontrolled stop can lead to huge safety risks. Think about a crane just coasting to a stop. It creates a total lack of precision in automated systems. It's incredibly inefficient, and all of that jerking and coasting can cause serious damage to your equipment over time. So, this is where the engineers come in. The solution to this problem of inertia isn't just about slamming on a brake. It's a whole field of study focused on one thing: mastering the art of control. And this quote just nails it. In today's world, stopping a motor isn't something you think about last. A controlled, predictable stop is a core feature. It's just as important, if not more important, than getting the motor started in the first place. So how do we actually do it? How do we achieve that perfect stop? Well, it really boils down to two fundamental methods. You can think of them as the brute force approach and the more elegant finesse approach. First up, we have mechanical braking, and you're already familiar with this one, even if you don't realize it. It's the same principle as the brakes in your car. It literally uses physical friction, brake pads squeezing a disc, to physically force the motor's shaft to stop spinning. It's direct, it's powerful, and it's incredibly effective. Now, what's really clever here is that these systems are designed to be fail-safe. See, when the motor has power, an electromagnet is actually holding the brake open, letting it spin. But the second you cut the power, or if there's a power outage, that magnet lets go, and heavy-duty springs slam the brake shut. That friction brings everything to a screeching halt, which is exactly what you want for safety. Okay, so the other method is electrical braking. Now, this is much more subtle, almost like magic. Instead of using physical friction, it cleverly manipulates the electromagnetic fields that are already inside the motor. Basically, it turns the motor into its own brake, creating a stopping force that works against the rotation, all without any parts ever touching. And this is where modern electronics are a total game changer. A little box called a variable speed drive, or VSD, acts as the brain. It can manage those electromagnetic fields with incredible precision. This lets you do cool things like a soft stop, where a machine glides to a perfectly smooth and gentle halt. So let's put these side by side, because this really shows the trade-offs. Mechanical brakes are amazing at holding a load completely still. That physical lock is unbeatable, but those moving parts wear down and need to be replaced. Electrical braking, on the other hand, has virtually no wear and can even recapture some energy. The catch? It needs a constant supply of power to hold something in place. It's a classic engineering puzzle. Do you need brute strength or do you need finesse? Okay, so we've got these two very different tools in our toolbox. How do engineers decide which one to use? Well, it all comes down to what that motor needs to do. Mechanical brakes are the absolute kings when it comes to heavy-duty holding and fail-safe operation. Think about it. Cranes, hoists. If the power cuts out, you absolutely need a physical brake to grab on and prevent a disaster. For jobs where safety and holding power are everything, there is just no replacement for raw friction. But then you have electrical braking, which is all about precision and smoothness. On a conveyor belt, a soft stop keeps bottles from falling over. In a big pump system, it prevents a damaging jolt called a water hammer. And for any machine that's constantly starting and stopping, the fact that there's no mechanical wear makes it last so much longer. And all of this brings us back to the real heart of the issue.
Because it's not really about one type of brake versus another. It's about something much bigger. At the end of the day, the hidden art of the stop is really the art of control. The safety, the precision, and the efficiency of so many systems that we depend on, they all come down to this one simple ability, to stop a motor at the perfect time, at the perfect speed, again and again, without fail.
It's this incredible technology that's just hidden in plain sight all around us. From the elevator you took this morning, to the robots in a factory, even the fans inside your computer. So next time you see something come to a perfect, smooth stop, you'll know a little bit more about the amazing engineering that made it happen. Makes you wonder what else out there depends on getting that stop just right.